at the University of Campinas. Recently, he started working as an intern at the Brazilian synchrotron light source. And this is with the Electronics Instrumentation Group. In this conference, Lucas will present to us his new results on the modelling of the fast orbit feedback system at SIRIUS. Thank you, Lucas.
Hello everyone, my name is Lucas Pelike and I'm from the Brazilian synchrotron light source, and today I will be talking about modeling of the SIRIUS fast orbit feedback control loop. I'll begin my presentation with a brief overview of the SIRIUS accelerator, then talk about our proposed model for it, talk about our system identification experiments, and then show our method for model evaluation. I'll finish them with some conclusions and pass up the references I cited. SIRIUS is a 4th generation light source located in Brazil. It has a ring with about 500 meters of circumference and a beam with 100 milliamperes. It is expected to increase after an RF cavities upgrade. Its fast orbit feedback system currently employs 78 fast correctors and 80 BPMs. Note how those two dimensions give us the size of our model system. We target an orbit disturbance attenuation of up to about 1 kilohertz. It has an update rate of 48 kilohertz. And if you it's a new system as well, that is in operation since 2022. And if you want to see more technical details, implementation, processing network details, etc., please see that article that was published in Inca Labs last year. The objective of this work is to build a realistic computational model for the FOF. Here is our proposed basic structure, which follows the expected feedback loop format. It is naturally always transfer functions shown are naturally matrices since we work with a multiple input, multiple output binary system. We have orbit setpoint input, a noise input, a disturbance input, output channel performance output, that is a performance channel, and naturally we can put analysis points at every wire shown. I'll begin talking about our systems plant, which has as input current set points and as output beams or beams orbit. The plant is constructed as a matrix multiplication between the measured orbit response matrix extended with this vertical column and a second matrix built by the fitted models for the correctors and an H function that models the phase through orbit transfer function. We did it that way because you can have the gains, DC gains at one matrix and the dynamics model in the other. General format for H of Z may be found in a paper published by the APSC. It is cited at the ending. In the results shown today and in our paper, we consider only the restriction to the AOIs. I will talk a little bit about our controller as well. In the same way, it follows the basic interval controller format, as almost I think every other fast orbit feedback system uses. It has a optional shaping filter, which has some filtering arrangements. It has a gain matrix that is built in a way that we can apply different gains for the vertical and horizontal planes. We also use a correction matrix that is obtained from the pseudo-inverse of the orbit response matrix, and also the basic discrete controller, the integral controller. A final addition to our model are these what we call weighting matrices that are placed in ways that we can, for instance, customize noise input to our system in order to do simulations, test some robustness or optimization considerations. We also have WFD, WFZ, for instance, to excite our system in a given direction and project it on the outside for Z. We did some system identification experiments because our correctors have some discrepancies, especially in the high frequency range. Here we have what I call a normal subset, and then here our weirdest subset of frequency response. For these experiments, we used pseudo-random binary sequences, derived signals. We do them with periods of 127 steps, and each step was composed by 3 samples. We in total applied 524 periods, and then averaged them all to one equivalent sequence. We apply 2 parameters and measure them at EPTMs. We apply a zero-gauge controller to have an open-loop transfer function. Then we use very basic ARX, autoregressive exogenous inputs models to fit our measured data. They are very simple, but good for our purposes too. We use 6-degree polynomials and a delay of 2 samples. And with that, we obtain reported fits with about 90% of accuracy between responses predicted by the model and what we measured in the real system. Each fit gave us one of those ALIs I showed previously. Now I will introduce our method that we use to evaluate. Standard tool analysis of MIMO systems are singular values, especially how they change in frequency. We again use PRBS-derived signals with parameters N and D, and controls the total period, and D controls saturation, or how many samples are held constant. A friend of mine made some drawings to help me visualize the idea better, and each block here represents an input signal and what we measured as output. All the excitations were made of modes, for instance, extracted from singular value decomposition of the response matrix. Yes. After exciting the system in those roller directions, we joined in matrices, building a sequence of matrices. In each column here represents an output to a given mode. And then we took the discrete Fourier transfer with regards to time, building what we called, informally of course, FFTQs. Here we represented the Cartesian product between the indexing set, the column lambda, for instance, and the slices in the algebraic frequency domain of those previous matrices. The next step was to, for each sample, calculate the product between the output matrix for a given sample and the pseudo-inverse of the related input matrix. Thus, building the J of chi-line matrix. Again, it is a sequence of matrix since we are varying K. Final step is to calculate the singular value decomposition of those G of Ks, thus building singular values or approximating them of our system, approximate singular values of our system. Here we have some results for our open loop experiment. In yellow have this method I described applied to the real system, and blue using the MATLAB function sigma, which does kind of the same thing. You can see some general agreement between those two curves, several curves, which one represents the value of those two. Our predictor response by the system and what we achieved with the machine. There's a dip here around 10.1 kilohertz that we cannot explain, but we think that is due to some experimental error. We then did almost the same thing using a Caesar restriction, where we used only one corrector and one ppm to measure the sensitivity. Input signal was orbital disturbance with about 5,000 nanometers. And you can see again a general agreement between what we measured and what the model predicted. There's a crescent peak about 10 kilohertz that is consequence of our D value selected previously. It does not really affect our conclusions because our main figures of merit are in a range well before the numeric anomaly, mainly maximum amplification and crossover frequency. And since we you can adjust that for with changing B value. It doesn't really matter in our case. I can go in more details if you want later. Now the results for, again, this is a restriction, but a vertical plane. It again has a grid agreement. And now some simulations using the whole MIO system, again, in sensitivity. In blue, we have the real model using all matched correctors, and an ideal case in orange using matched correctors. There are some very weird large amplification peaks around here that we currently cannot explain, but it doesn't appear in our real system and apparently doesn't affect performance. Our main hypothesis to explain this is that in simulation we excited some directions that do not occur in normal practice. I think we did a very good job since SIRIUS is currently going on an upgrade, and so I had about 3 months to do all experiments since the machine time studies were limited as well. And our proposed model allows a realistic analysis of SIRIUS fast feedback, for example, capturing discrepancies between fast correctors. Our noise and disturbance inputs allow us to analyze sensitivity and noise rejection for a given configuration. We also can make some robustness considerations by studying gain increases of the model instead of trying them out in the real machine. We also presented an easy-to-use evaluation technique, and future work will be concentrated towards a better understanding of the interaction of the low-level RF loop and optimization tests with those shaping filters as shown before. Here are the references I cited, and all the code we used is also available at our repository in GitHub. We really like open source and hardware collaboration, so if anyone wants that link, you can just come talk to me. Thank you everyone for listening, and thank you my Brazilian colleagues for all the help. Thank you everyone.